Hello friends, welcome back to another exciting tutorial on game hacking. So in this tutorial we are going to learn much in detail about the system and the different types of micro operations and the opcodes which we see. Basically I'm going to teach you four different kinds of logical operations, namely NOT, AND, OR and XOR. These are the things which we will be seeing most of the time in the assembly language, which we will be getting frightened by seeing most of the time. So let me begin by teaching you by giving a graphical representation of what happens with each of these. First, let me show you a NOT gate, and we are going to see what all the different operations which it does for us and what all happens with a NOT gate. So let me quickly draw it. A NOT gate will be represented by a triangle and a NOT before it, and it has a single input and a single output, and all these operations which I am going to show now are done on a single bit. So let's say I'm going to give a input of, let's say, a variable, let's name it as x, then the output of it would be x bar. The output would be x bar. Let's make it like this. So let me draw the different, and now as we are dealing with binary, let me put an input. So let's say I'm going to give an input of x, and the output of the operation would give me x bar. So as we know that the computers work in binary, we'll have only two different values for this x over here. Either it could be 0 or 1. Let me write and show 0 or 1. Let's say, let me take it as a 0. When the value of x is 0, then the output would be obviously given as 1. So 0 flipped it and we got 1. And when the input is given as 1, then the output would obviously be its flipped form, so 1. This is the thing about a NOT gate, and this is the thing when you observe a NOT opcode, when you see a NOT in your opcodes. And I think the NOT is not used nowadays. So the NOT opcode might look like this. Let's say I have a register NOT of, let's say we have a register EAX. So what this opcode might do is that it might flip all the bits, as the EAX is of 32-bit register, so it will flip all the bits which are present in the register. That's the thing which is done by a NOT. And now let's move on to the second opcode. Let me first write down all the different kinds of things. NOT, we are going to discuss about the NOT, we are going to discuss about the AND, we are going to discuss about the OR, we are going to discuss about the XOR. Remember, this is the most hardest thing, and which we would find in the encrypted value types of things. So your encryption would be done by any one of these three, the bottom three, and they might use an AND or an XOR. So the NOT is over, and now coming to the AND. An AND works in this way. So whenever it sees the two inputs as one, then only, whenever it sees its two inputs as 1, then it gives an output of 1. So this is the logical symbol for the AND gate. It might look probably like this. Okay, it's fine for our understanding. And an AND opcode takes two registers or two inputs, and it gives a single output to us. So let me name those inputs as, let's say, x. Forgive my handwriting for this. Let's say the second one is y, and let's draw a table for it. So let me take the different values of x and y. And as I have previously told, a single input of x variable can contain two values. It might be either 0 or 1. So let us write it. Either x could be 0 and y could also be 0. Let me put it an AND over here. This is the output of an AND. So as I said, an AND opcode checks if both the, let me first complete the table. When x can be 0 and y can be 1, and the other thing is x could be 1 and y could be 0, and the last and final thing of possibility is that both the x and y might be 1. So your AND gate takes any, based on the inputs, it does an AND opcode or operation, and it checks that if both are 1, then only it results into a 1, and in all the remaining cases it results into a 0. So this is the table for an AND. And next coming AND is over. Now we are going to talk about OR. So the OR is, as the name suggests, the OR means either x or y, and the let me show this symbol for it, and let me all this. Let me do it again for your convenience. Why I am teaching all this? Because we are going to come across these things in our games, and the games which we are going to hack. Let me make an OR gate, simple OR gate. An OR gate looks something like this. An OR gate looks okay. It's a bit fine. It has two curved paths. Forgive my drawing if it is not okay. An OR gate has two, what we can call this as concave side. This is a concave side and this is a convex side. So alright. So we have two inputs for this as usual. As an AND, it takes two inputs x and y. It gives an output x or y. So the way OR works is that it checks if any one of the two inputs is 1, it results into a 1. So the first input given is 0 and 0. 0 and 0. So none of these two inputs is 1. So it returns a 0 for us. And as you can see in the second and the third case, in the second case the y value is 1, so it returns a 1. And in the third case, as the value of x is 1, it returns a 1. And in the case of fourth one, as both are 1, it anyhow returns 1. So the OR works in this way. If it sees at least one of the input as 1, it gives an output as 1. This is about OR gate. Now coming to the most dangerous gate, which we will find at most of the time, and which it will make us fear for most of the time. This I saw many times. This is used for doing encryption of values and all that kind of things. So we should learn about it in more detail. Let me first draw an XOR gate. An XOR gate, as the name suggests, it's exclusive OR. It does an exclusive OR operation. So its symbol looks similar to the OR gate. This is an OR gate. Sorry. Okay, this is an OR gate, and then it has another curve over here before the OR. So sorry. This is the symbol for an XOR gate. So in the similar way to the OR gate, this also takes two inputs, one from the x and one for the y, and then it gives the output. and then let me write it as XOR. So the XOR works in this way. Let's say I have an object over here. This is my analogy which made me easy to understand. Let's say this is one object, and let us say this is a second object. So, and if you do an XOR is denoted with this symbol, a plus and encircled. This is a symbol for an XOR. So if one input and the second input are different, then the output result of this is gonna be 1. And if both are same, let's say 1, and then let me XOR it with the same thing, or else let us do it over here only. If I do 1 XOR with 1, so as both the inputs are same, we are going to get the output as 0. That's the thing. Or else you can even think it as, if two twins are seen by an XOR, it zeroes them out. Two twins, so it might be both zeros or both ones. So let me so as we can see, this is 0 and 0. So as I said, if both the inputs are equal, then the output of it would be 0. And here if you see, both the inputs are different, so it returns you a 1. And here also x and y inputs are different, so it returns you a 1. And in the last case, both the inputs are same, and it returns a 0. This is the thing how XOR works. And all the discussion till now which I did is on bitwise operations. All this, name anything, let's say or and XOR or not, all these four things are working on bitwise level. So whenever you see this kind of opcodes in your assembler or cheat engine, what I will say is, you convert both the operands into their binary bit level and do their operation, then you'll get a clarity about this. This is the thing about the operations or opcodes which we see. And now coming to the registers, I would like to explain about the registers. Let me show you first the register. Let us take this bigger one register. Let us make it as a 64-bit register. 64-bit registers are denoted by, let's say, RAX, or else it might be RBX. So the first letter would be an R, and the second letter denotes the type of the register which is having, and the X means that it is an extended register. So RAX means write extended. A is for accumulator. In the similar way, if we have a RCX, it is used for counting. It is used as a counter variable. So let us take an RAX. RAX is of 64-bit register. So this 64-bit register can be broken down into two 32-bit registers. So let me name it as, this is a 32-bit register and this is a 32-bit register. This lower part of 32-bit register is called as EAX. EAX means extended accumulator register. And this 32-bit register is again divided into two 16-bit registers. This, this is the first 16th part, and this is the second 16th part. So this 16th part is, the lower 16th part is again named as AX. So this is a AX part, and then this 16-bit is again divided into two 8-bit registers. This is a 8 and this is the second 8, and each 8 is named differently. This first 8 is called as, since it is in the the numbering would be done as here. Let me do it over here. The numbering will be like this. This will be the 0th bit, 1st bit, 2nd bit, 3rd bit, and it goes on from left to the right. So the values in the 8th bit are up to 1 till 15. This will be starting from 8 to 15. So these values are higher than these values. So this left part of 8 bit is named as AH. AH means A high, and coming to this last part, this is named as A low, AL. So each of 8 bit. So based on the requirement, the processor decides the register which it needs to use. So if it is dealing with 64-bit values, then it selects the whole RAX, and then if it wants only 32-bit of memory to be used, then it uses only AX. And then coming to these figures, the 8 let's start from the highest order. Let me show it in a notepad, it would be better. A 64-bit value, let me increase the font as that you can see. Okay, the 64-bit value is named as D word, which means that a double word, and a 32 is named as 64 is named as quad word, 32 is named as double word, and a 16-bit is named as a word, and an 8-bit as we all know, it is a byte. So in this way the whole system is naming itself. And we sometimes come across something like in our code that we'll have a move, we'll have a D word pointer of EX plus 32, something of like this kind, and we'll have some random values. So the significance of this is that it is trying to access it, like it's trying to put this value, make it into a double word type of value, convert it into double word, and then put over into this. And then coming to the importance of these square brackets, as the computers have the registers, these registers have multiple purposes. Like a single register, let's say, let me make this as a name it something. So this can be used for storing either like a register, RX can be used either for storing data, or it can also be used for storing the address of some different thing. So when it is used for storing data, it is directly used as RAX, and when it is used for referencing something, it is used inside a square brackets, which means that RAX actually holds the address, but then these square brackets would give you the let's say the value inside the address. And if you have any knowledge of something like C or C++, a light knowledge also, we have something called pointers in it. So what a pointer holds is that it holds the address of some variable. Let's say I created a pointer int a is equal to, and then we give the address of some other different memory in the memory region, and then this a holds the address of the b. So whenever you want to get the value inside a, we write star a and printf or something. So this star a means the address of a, the star is used for dereferencing the memory and to get out the value of it. So star a is used as get me the value pointed by the a. In a similar way, these square brackets are used in such a way that EAX plus 32 is a pointer of type D word, and then these square brackets will tell that get me the value inside that, or else if it is used on the left hand side of the comma, put the value inside this pointer, put this value inside this pointer of D word type. this type here it is like int, like that it is a divert type of pointer. That's the thing about the pointers and the registers. And now let's take a break now and let us return back after 5 minutes, and then I'm going to continue and we are going to hack the Assassin's Creed game after we continue from a break. Alright, welcome back friends, and now let's start hacking the game Assassin's Creed. Let us wait for a second for it to load up. I have muted down the volume of the game to not get any issues and disturbances in regards to our video. Alright, now we are going to hack the amount of knives which we are having in this game. A friend of mine has requested me to do it, so I'm doing it. And I hope that you are having a little idea of what all I have said till now, at least the basics of this logical operations. Alright, we are into the game, and let's see the count of the knives which we have presently. You can see that those are 20 at the left bottom corner of the screen. So we have a count of 20 knives at present with us. Let's get out of the game and shoot up the cheat engine. And in this game the value of the knives or the knife count is an encrypted value, so you can't just directly put the value of, let's say, 20 over here and directly do a 4-byte scan exact value. No, you're not gonna get the exact value of 20 as it is encrypted. The only thing which we could do is select the type of the value into all and put an unknown initial value in the scan type. And the other thing which I suggest you to do is go into edit settings, and then you go into the scan settings and then check all the boxes over here. With the default setting of the cheat engine, some of them might be unchecked. You check all of them. The main aim of to do the all value type scan is that you want to get the whole values which are present in the whole, I mean the total values which are present in the memory. So put an value type of all and the scan type of unknown initial value. Do your first scan, and then you go back into the game and then resume the game, and then you try to change the number of knives which you have. So let me shoot out a knife, and now we have 19 knives. So get out of the game, and then now as I said, you can't directly put a 19 over here and you can't do a search for it. The only thing which you could do is only changed or unchanged type of scan, as it is encrypted. So you should do a change value scan and do a next scan for it and wait for it. And then I never recommend you to do a all type and unchanged value type scan. The reason is that the all and unchanged would become a tedious process for your processor to search for in the whole RAM or the main memory. See, the change value is only taking so much amount of time, and if you have put unchanged value type, it might take so much of time. So alright, the scan is almost over. Yes, it's completed. Now what we need to do is go again into the game and then spend another knife, change, so the value of knives has been changed. So again, scan type, you make it as change value and do a next scan. That's what we can do with this type of values which are encrypted. and see how slow the system might become while doing these type of scans. So I might pause the video. I'm going to pause the video and I'll be back after getting the exact value, I mean the encrypted value of it, and then we are going to continue with the video. Alright friends, I went ahead and brought down the results by some more, and then we are now again going to bring them. It's almost 61,000. I am going to make it a little bit and then we are going to continue. Alright friends, so I brought down them to a much lower value and I have found out that this corresponding value, see 16,402, this value is changing our exact value. So let's try doing something with it. Let me try to fix it and see if our value goes down. The value is 18. So it became 17. Okay, it became 18. So alright, we finally found out the value. That's it. You see, the value is either fluctuating between 17 or 18. That means we have found the exact value. So what we could do now is we are going to do, as usual, as a general and common step, we are going to do a find out what writes to this address, and let's go into the game and spend a knife and see which instruction is writing to this. That's it. See, the most dangerous instruction XOR has popped out, and let's see what is happening in the code over in the disassembler. Let me unlock the screen. So this is the thing. So the ESI register is XORing our present value and giving us the result, and let us see the values of the registers at that time. So the ESI is having 3 followed by 4 zeros, and then so ESI is being XORed with our present value. And then I have also found out that, see, this value, our present value, is being brought from a stack. So as the full form of EBP stands for extended base pointer, so these values are being brought from somewhere in the stack. See, as you can see, so that means that as this is an encrypted value, you see, I'll show over here, see 16401, it has nothing to do with our present value. I'll show you the present value. The present value is supposed to be 17, but then it is encrypted by this XOR instruction and it is put on into an 16401, and then you can also see that it is being brought from a stack. So this corresponding code which we have found isn't the code which is writing, it is the code, let's say it is writing to the display. So we need to go backtrace it and go to the place where it is being put onto the stack before it is being encrypted. It is one way. You could do it by going into the break and trace instruction and do all this kind of stuff, but then I have found that instead of we doing all that things, we could directly go and see what accesses this address, which will directly give the instruction which is writing it onto the stack directly. Alright, see, let us examine each of these. The first instruction has been run so many times, so this might not be the one, and the second instruction and the remaining all instructions are being run only once. And see, this was the instruction which we have previously seen, XOR ADI plus 04 comma ESI. So this is not the one, this is gone. So let us start trying from top to bottom. Let us see this instruction in the disassembler. So see, our value is being brought into ECX, and then some changes are being made to EBX and EDI, and then our present value, see, ECX value is being ANDed with 4 zeros followed by 3 and triple F. Let me shoot out the calculator and let us see what is happening over here. And first, before doing this, you might always check that how many instructions are, how many values are trying to access this instruction by just going into the game. And I have found that only one value, that is our present value, is only using this. So this isn't a shared opcode, so we can directly do an auto assemble, no need of any comparisons or anything. So this ANDing is the thing which is happening with our ECX value. Let me shoot up the calc. Wait for a second. That's it, the calc is up. So our present value, let me show it in the memory viewer. The present value of ECX is being ANDed with 3 followed by 3 F's. So let me copy this 3 followed by 3 F's, what it is going to mean to us. Let me put it in the calculator. That's it. 3 followed by 3 F's is equivalent to binary a 4 byte number, that is, this is what which it has. And then let us see our present value. Our present value you could see over in this. Our present value ESI plus 1A, that is supposed to be this. So 16399. Let us convert it into binary by putting it into the calc. So the operation which we have seen is that it is being AND. So as I have said previously, the AND operation is a bitwise operation. Let us put our value and see its binary value. So this AND, it is being ANDed with, what we have seen was 3 and followed by 4 F's. This is what which is happening. Let us see the answer. So the answer is F. That means in decimal it is supposed to be 15. So if you see in the game, the present current value is 15. So we are having a value of 15. So that means that this AND operation is doing the AND of ECX and this 3 followed by 4 F's, and then giving the output of that AND as it is being again pushed onto the stack over here. You can see it over here. See, it is being ANDed and then it is being put into EBP minus 04 and EBP minus 020, and then it is being again pushed onto the stack. So that means that this AND instruction gives you the present value of this. So and this AND instruction is also being used as an subtract over here. So 16383 is the decimal equivalent of 3 4F's. Let me show it to you. So let me say 3 followed by 3 F's I have. See, you can see that its decimal equivalent is 16383. So that 16383 is ANDed with ECX. ECX is of 163 followed by 99. So so if you subtract this value, or else 16399, if you subtract from 16383, the result is again, see, the result is 16. So what this AND operation is doing is that it is giving the subtraction of these both. So what we could do is, we don't want any knife value or else the count of knife not to decrease. So we can either knob out this AND instruction, which would not decrease our value, or else you can just replace these 3 or all these things with 0, or else you could simply write a script for it. So the script might be looking, let's make it more easier. Let's wait for, just wait for a second, I'll complete. And then I like to do it by using code injection. The reason is that it will be easier for me to read. Some people I have seen that they are using array of bytes injection, which in array of byte injection what it happens is that the cheat engine searches for this particular 81 E1 FF 3F 0000. It will be searching for that and then it is going to inject. But then in this code injection what it does is, it directly checks for this code ecbsp.exe plus so and so offset. See, you can see that it checks for this offset, then it jumps to the new memory which is over here. Then as nothing is there over here, it comes over to the original code and then it exits. That's the thing which happens. So let me take out all the unnecessary things which I don't need. We just need to have that new memory, no need of even exit. I directly wanted it to be executed. So the code is that I'll go over here, jump to the new memory, that will take it to over here, and then I don't want it to be ANDed. Let's start by taking two F's. We'll take two F's. So if I take two F's, and then let us see its value. I have a value of 3F00 now, and I want to AND it with the present value. The present value is 16399. So let me AND it with 16399. See, so the value to be subtracted has become 0. So the value to be subtracted, as it has become 0, there is no subtraction which is going to be performed. So I have put two zeros over here. That's the reason. So, and it is going to do this, come over here and get outside. That's it. Let us assign it to the cheat table and try out if this works. Let's stop and close this one, and then let us try our code. The previous value was 15. Let us see. See, we have finally achieved the infinite number of knives. As you can see that the value of the knives is not being decreased from 15. That's it, we have achieved infinite number of knives. But then you might also go around and dig with this code, and you might be wanting to get a max value. Let's say I want to put a value of, let's say, 1000 knives, or else 100 knives. So what you should do is you should go into memory viewer, and in the memory viewer the value of ECX is being brought from ESI plus 1A. See, as I have previously explained, the word pointer, so this value, as I said, word is of 16-bit. The 16-bit value is being put into ECX. That value is being AND over here. So you want to put your value over ESI plus 1A. So you could write a code over here. So as like this, I want to move a value of, let us make it into an int of, or else that's it, an int of, shall we do it directly, or else I want to have a value of 99 knives, and then that value should be put in ESI plus 1A, and the type of it is word pointer. That's it. I want to move a value of 99, which is hex 99. That means it's binary, that is decimal equivalent. Let us see, 99 hex is implies 153, or else let us make it into 16399 is the present value. Let us say that 16399 is corresponding to a value of 15, and I want to have a value of 99. Let us say I want a value of 99 over here. So what might be the value over here? Let us just do a simple calculation. Let me see the difference between 15 and 99. Let us 50, so 84. So let us try to add a 84 to 16399. So let us add 16399 plus 84, which results into 16483. So for 15 number of knives, if it has 16399, for 99 number of knives I should be having 16483. Is it that? Yes, 16483. So I want to put a value of 16483, and its type is of int. Let me put it, int of 16483. That's it. So this value is making the subtraction to be 0, and this instruction is putting the maximum value into that. That's it. Let's try to attach the script. That's it. Let's see how many value of knives do we have. And you might be thinking that suddenly my value isn't changing. So what you need to do is you need to refresh the value. Just go into the table, or else just exit out of the screen and just come back to the screen and look, or else wait for a second. I think we haven't, oh, that's the thing, we haven't used the script, we have just attached it. So let us use a knife and see. the value to be flushed over. See, the value has been changed, so we have got 99 number of knives. That's it. So finally we have got 99, and then these 99 are infinite. You can be using this how much ever you want, and I have found that the maximum value is only 99, not above 99. Though you put it above 99 also, the display code is going to show you only 99. That's it. You got infinite number of knives. This is an indirect way, I mean lengthy way of doing it. So what I have found from my friends and the other very good efficient programmers is that what they do is they do direct byte manipulation. What they see, the code which we have written has only the thing to do with these two F's are to be changed into two zeros. So what they do is they will directly go into over here, and then they will directly make these two F's into zeros. I will show it how it is done. And I also started doing this, and the reason why it is done is it will make your code more compact, more simple and more efficient. So in that, no need of doing all these things, nothing is needed. No need of having a new memory to be allocated, no, nothing is needed. So you have to go directly over there and see. Let's copy the previous instruction. So the db means that you are going to declare a byte. So whenever you enable the script, you are going to go over till here, and then after the colon, whatever is written, you are going to execute it. So db instruction declares a byte. So 81 corresponds to AND, E1 corresponds to ECX, and this corresponds to the value which is towards the after the comma. So AND ECX, and as we know that the computers read from right to left, so these two zeros over here correspond to the first two zeros over here, and the second pair of zeros correspond to the second pair of zeros over here, and then we get a 3F over here which corresponds to this 3F, and then lastly we have these two F's which are corresponding to these two F's. So we want to change these two F's, these last two F's into zeros. So the F's before 3F are need to be changed. So just let me put two zeros over here and let us see what happens. That's the thing. So let us try the script and then let us see what happens. Then I'll explain what is happening. And now you try to shoot the knives. See, again we are having an infinite number of knives. So this script, what it has done is that, you see, previously before this AND instruction it has 8 1 E1 FF 3F followed by 4 zeros. Whenever I enable my script, see, those two F's are changed into two zeros. See over here, directly those F's are being changed into two zeros. If I disable, they again return back to two F's. That's it. This is the efficient way to do your scripting, and moreover you can directly do much more things. See, let us say that 7EF0D4 is pointing to 81. So you want to go to FF and change it to 00. So 81, let us say, as computers start counting from 0, this is 0th one, this is the first one, this is the second one. So I want to go to the second location and then make it into a 0. So, and I want to go to the second location from the origin and make it into FF if the script is disabled. So see how simple the code looks. Go over till here and put two zeros over here, and whenever you disable it, go over till here and to put two F's over here. That's the smallest script which we can do. And if you enable the script, observe the changes over here. These two F's are going to be changed into two zeros. See, tada, these two F's, these two F's have been changed into two zeros suddenly. That's it. So finally you have achieved the infinite number of knives with a simple and efficient thing. That's the thing for this video, and in the next video I'll be trying to explain you how to do trainers, and that's it. So in this way we are going to get infinite number of knives. So this is the AND operation. That's it. And coming to the things which we have learned in this video are that, firstly we have learned about the different types of logical operations, or XOR, and not. And then now we have hacked the amount of knives in this game. And then I like this game so much, I like to play it. That's the thing for this video. Thanks, and we'll meet in the next video. And like this video if you liked, subscribe for my channel, and thanks for watching. Bye bye.